Hello, my name is Martine and I'm from the University of Amsterdam. In this work, we present a novel method for self-supervised video representation learning. The basic idea of contrastive instance learning, also known as instance discrimination, is to learn an embedding where similar instances are close together and dissimilar ones are far apart. By using augmentation on the same sample, we obtain multiple views of a sample, which will result in a high similarity score. Contrasting with views that belong to different samples will result in a low score. A downside of this method is that we need to compare every instance with many others before we can get good representations. This means that in every iteration, we need a large pool of negative examples. Because all negative examples are treated in the same way, we only use similarity on the instance level. For example, two different clips of people cycling will be treated as dissimilar. Also, this method uses only visual similarity, while video can provide us with more information, for instance with audio or optical flow. In this method, we use RGB and optical flow as views for contrastive learning. Our key insight is to learn from similarity between groups of instances by including mappings to prototypes. A prototype is defined as a representative of a group of similar features. First, we train each model on their own feature in the first stage, single stream. Then, in the cross-stream stage, we optimize RGB using views from both models. Next, we optimize flow in the same manner, using both feature types. We can repeat this alternation process if needed. For downstream tasks, we can use the average of both models together or just the RGB model. As the RGB network has learned motion information from the flow network, we can avoid expensive optical flow computation by using this network only. The cross-stream training starts with our input video. 4 different views are created by using data augmentation on the RGB frames and the optical flow, and the views are passed through the encoders. Now the first step is to assign features to prototype vectors to get 4 assignments, 1 for each feature. The prototype vectors are randomly initialized at the start of training. The mapping is found by using an optimal transport solver. Because the model now needs to predict the assignments in the next step, we make sure that we assign features uniformly with the epsilon parameter, to avoid the model simply assigning all features to the same prototype. Now we have assignments. We let the model predict each of the 4 assignments. Every time it predicts 1 assignment, it can only use 3 other features that come from different views of the same instance. The model should therefore predict the same prototype for all 4 views. The loss consists of the 4 prediction losses together. Overall, the features are contrasted indirectly by contrasting their prototype assignments instead. In doing so, we avoid unnecessary comparisons. Pre-training was done on UCF, and we evaluated on 2 downstream tasks, action recognition and video retrieval. Comparing our models with other methods with the same backbone on action recognition, we perform better than most other visual-only methods for both backbones. We also outperform several methods that use audio in combination with video. The code for this paper can be accessed at this link or by scanning the QR code. Thank you for your attention.